Welcome back, everyone, to the deep dive. We're going to be looking at something that's super important today in software development,
hmm
building those, data-intensive applications. And to help us kind of unpack some of the big ideas,
Right.
we're going to be diving deep into a chapter from designing data-intensive applications.
Yeah, it's a really cool book.
Yeah, it's one of those books that's like a must-read for like any software engineer.
Yeah.
Um, So before we jump into all the nitty-gritty details, I kind of want to get your take on like the big picture here.
Sure.
What's the common misconception that, a lot of developers have
Yeah.
when they first start thinking about building these data-intensive applications?
Well, I think a lot of people, when they first start out, they kind of think about databases, message queues, caches, all these different tools as like separate things.
Right.
Like, okay, I need a database, so I'm going to go pick out a database.
Yeah.
I need a message queue, I'm going to go pick out, Kafka or RabbitMQ or something. But the book really encourages you to think of them as all part of one big data system.
So it's not just about picking the right tool for the job. It's about understanding how all these tools fit together.
Exactly. Yeah, and it's like building like a complex piece of machinery, Like you wouldn't just like slap together a bunch of random parts,
Right.
You have to think about how they all work together.
Yeah, it's like building a high-performance race car. Right?
Right.
You're not just gonna like take the biggest engine and like slap it in there and expect it to work.
Right.
You need to carefully consider all the components, like the transmission, the suspension, the aerodynamics,
hmm
like how they all interact and how they work together to create a system that's like optimized for,
Yeah.
speed and efficiency.
Exactly. And that's a great analogy because it really highlights the importance of like the system as a whole.
Right.
Right. It's not just about individual components, it's about how those components work together.
So speaking of like the system as a whole, this chapter kind of zeroes in on three key qualities that we should be striving for when we're building data-intensive applications:
Yep.
reliability, scalability, and maintainability.
hmm
And like when I think about those, like those are all qualities that like I want in any software system.
Absolutely. Yeah.
But let's start with reliability.
Okay.
And like we all want our systems to work, obviously.
Right.
But what does it actually mean for a data-intensive application to be reliable?
So I think for a lot of people, when they think about reliability, they think about like, okay, is the system up?
Right.
Is it running?
Is it on fire?
Yeah, exactly.
Okay.
But it's actually much more than that.
Okay.
It's about ensuring that the system continues to function correctly, even when things go wrong.
So it's about like anticipating those unexpected events.
Right.
Like, you mentioned hardware failures, software bugs, even like human error.
Oh yeah, human error is a big one.
Oh yeah, especially human error.
Right.
Like I've definitely been there where I've like accidentally like, deleted a database table or like, misconfigured something.
Yeah.
So it's about designing systems that can withstand those inevitable hiccups.
Yeah, and it's not just about like surviving those hiccups, but continuing to function correctly.
Right. So it's not just about staying online. It's about making sure the system's actually doing what it's supposed to be doing.
Right. And doing it in a way that like, meets the requirements of the application.
So how do we actually go about making our systems more resilient to these kinds of failures?
Well, there are a lot of different strategies you can use. One common one is redundancy,
Okay.
right? So you have multiple copies of critical components. So if one fails, the other one can take over.
So like, for example, RAID configurations for disks or dual
Mhm.
power supplies for
Yeah.
servers.
Exactly. Yeah. And even things like, backup power generators for data centers.
Okay, so it's about having those backups in place just in case something goes wrong.
Right. And it's not just about hardware redundancy, it's also about software fault tolerance.
Okay.
So designing your software so that it can handle the failure of entire machines.
So even if like an entire server crashes, the system can keep running.
Right. And there are a lot of different techniques for doing that, like replicating data across multiple machines,
Right.
using distributed consensus algorithms to make sure that all the machines have the same view of the data,
Right.
and implementing graceful degradation mechanisms so that if part of the system fails, the rest of it can still function, maybe at a reduced capacity.
So it's almost like building a self-healing system.
Yeah, that's a good way to think about it. It's like the system is designed to adapt and recover from those setbacks.
Wow, that's pretty incredible. So reliability is not just about preventing those outages, it's about ensuring that the system's actually doing its job correctly, even when things go wrong.
Right. It's about building those robust and resilient systems that can handle those inevitable failures that we're going to encounter in the real world.
So now that we've kind of covered reliability, I want to move on to scalability, which is, I think, another huge challenge when you're building these data-intensive applications.
Yeah, absolutely.
We've talked about, these applications needing to handle like huge amounts of data and traffic.
Right.
Um, so how do we actually build systems that can like handle that kind of growth and scale effectively?
Yeah, so scalability is all about handling growth gracefully.
Okay.
Right. As your application gets more users, as it has to process more data, as it has to handle more traffic, it needs to be able to adapt.
Right.
And in order to understand how well your system is scaling, you need to understand load parameters.
Okay. Load parameters. Break that down for me. What are load parameters and why are they so important?
So load parameters are basically the things that tell you how much stress your system is under.
Okay.
Right. So things like requests per second.
Okay.
How many requests is your system handling every second?
Gotcha.
The ratio of reads to writes in your database.
Okay.
How many users are active at any given time?
Right.
Even things like the fan out in a social media application.
Fan out. Okay. That one sounds interesting.
Yeah.
Can you elaborate on that?
Yeah. So think about like Twitter, right?
Okay.
Every time somebody tweets something,
Right.
that tweet might have to be sent to millions of followers.
Wow.
Right. So that's a massive fan out.
Yeah.
And it creates a huge spooling challenge.
Right. Because you're essentially multiplying the workload every time someone posts something.
Exactly.
So by understanding these load parameters, we can kind of like anticipate how our systems are going to behave under different levels of stress.
Right. And it helps you pinpoint potential bottlenecks in your system,
Okay.
right? Like if you know that your system can handle a certain number of requests per second, but then you suddenly see that number spiking,
Right.
you know that there's probably something going on that you need to investigate.
So it's about understanding like those pressure points in our system and like knowing where to look when things start to go wrong.
Exactly.
Yeah.
And then you can make more informed decisions about how to scale your system effectively.
So it's not just about like throwing more hardware at the problem. It's about like understanding those underlying dynamics of our system and like making those smart choices about how to scale it.
Right. And those choices can involve things like, optimizing your code or changing the way you've architected your system or even adopting new technologies.
Right. So it's a holistic approach to scaling, not just a Band-Aid solution.
Exactly.
So we've covered reliability and scalability, and like those are both crucial aspects of building those high-performing data-intensive applications.
Yeah, absolutely.
But there's another key quality that like often gets overlooked, and that's maintainability. Right. Like, we can build the most reliable and scalable system in the world, but if it's a nightmare to maintain,
Right.
like it's going to be a huge headache down the road.
Yeah, absolutely.
So let's dive into maintainability. Like, what does it actually mean to build the maintainable data-intensive application?
So maintainability is all about making it easy to keep the system running smoothly in the long term.
Okay.
Right. And that involves focusing on things like operability, simplicity, and evolvability.
Okay, those are some big words.
Yeah.
But I think they all sound like good things.
They are good things.
Yeah.
Yeah. So operability basically means making it easy to keep the system running.
Okay.
Right. So things like monitoring, being able to see what's going on in the system,
Right.
being able to easily update the system,
Okay.
all those kinds of things that make it easy for like the operations team to keep things running smoothly.
So it's about like minimizing those operational headaches.
Exactly.
Yeah. Okay. And then what about simplicity?
So simplicity is all about like avoiding unnecessary complexity.
Okay.
Right. So making sure that the system is easy to understand, it's easy to reason about, and it's not overly complicated.
So it's not just about like writing clean code. It's about like designing the system in a way that's like inherently simple.
Exactly. And a lot of that comes down to using good abstractions.
Okay.
Right. So, hiding away the complexity behind those simple interfaces.
So we're going to we'll dig into abstractions a bit later.
Yeah, we'll definitely talk more about that.
Okay, cool. And then finally, what about evolvability?
So evolvability is all about making it easy to change the system over time.
Okay.
Right. As the requirements of your application change, as new technologies emerge.
Right.
You want to be able to adapt your system without having to completely rewrite it from scratch.
So it's about like anticipating those future changes.
Right, and building in the flexibility to adapt to those changes.
Okay, so it's not just about building a system that works today. It's about building a system that can evolve and adapt to the future.
Exactly. It's about building a system that can grow with your application.
So we've talked about these three key qualities: reliability, scalability, and maintainability.
Mm-hmm.
And it sounds like they're all interconnected, right?
Yeah, absolutely. They all play a role in building those successful data-intensive applications.
So we can't just focus on one in isolation. We need to consider all three of them together.
Right. And that's why this book is so valuable.
Right.
Because it really helps you think about all these different aspects of building these complex systems.
And like, I think it's really easy to get caught up in like, the day-to-day like coding tasks
Yeah.
and kind of lose sight of like these bigger picture principles.
Absolutely. And that's why it's so important to take a step back every now and then.
Right.
And think about these things.
And think about like the long-term health and maintainability of our systems.
Right, exactly. Because in the long run, that's what's going to make a difference.
So, we've laid out this like really important foundation.
Yeah.
And I think like this is going to be really valuable for our listeners.
Absolutely.
As we like continue to explore all the the nitty-gritty details of building these like data-intensive applications.
Right.
So let's dive into those details. Let's start with reliability. Like, what are some of the concrete steps that we can take to make our systems more resilient to those inevitable failures?
Well, one of the first things you can do is start thinking about those potential points of failure.
Okay.
Right? What are the things that could go wrong in your system?
Right.
And then how can you mitigate those risks?
So it's about like identifying those weak points and then figuring out how to strengthen them.
Exactly. And there are a lot of different techniques you can use depending on the specific failure mode you're trying to address. So, for example, if you're worried about hardware failures, like a disk crashing or a server going down,
Right.
then you can use techniques like redundancy.
Right, like we talked about earlier.
Exactly. So having multiple copies of your data, having backup power supplies, all those kinds of things.
Okay, so redundancy is a big one for hardware failures.
Right. But if you're worried about software bugs,
Okay.
then you need to think about things like testing and code review.
Right, so it's about like catching those errors before they make it into production.
Exactly. Yeah. And making sure that your code is well designed and well tested so that it's less likely to have bugs in the first place.
So it's about like building that quality in from the start.
Exactly. And
Okay.
then for human error.
Okay, yeah, that one's a tough one.
Yeah.
Because like humans are going to make mistakes.
Right.
It's just like it's inevitable.
So you need to think about things like automation and safeguards. Right. So, for example, you could have automated checks that prevent you from accidentally deleting data.
Right, like that confirmation dialogue that pops up.
Exactly. Or you could have a process where you need to get approval from somebody else before you can make certain changes.
So it's about like putting those guardrails in place.
Exactly. Yeah. And it's about designing your systems in a way that minimizes the opportunity for human error.
Right. So it's not just about training people and telling them not to make mistakes.
Right.
It's about building the systems in a way that kind of makes it harder for them to make those mistakes.
Exactly.
So it sounds like building reliable systems is really about this multifaceted approach.
Yeah, it is.
It's about redundancy, it's about testing, it's about automation, it's about careful design.
Right. And it's about understanding the different types of failures that can occur.
Right.
And then coming up with strategies to mitigate those failures.
So it's not just about throwing technology at the problem. It's about really understanding the nature of the problem and coming up with those appropriate solutions.
Exactly. And it's about recognizing that failure is inevitable.
Right.
Right. No matter how hard you try, things are going to go wrong at some point.
Yeah.
So it's about being prepared for those failures.
And being able to recover from them.
Yeah.
Quickly and gracefully.
Exactly.
So reliability is really about embracing that reality of failure and building those systems that can handle it.
Yeah. And it's about building those systems that can handle those failures without completely falling apart.
Right. So they can keep running even when things go wrong.
Exactly.
So we've talked about redundancy, we've talked about testing, we've talked about automation. What are some others key strategies for building reliable systems?
Well, one important thing is to have good monitoring in place.
Okay, monitoring. Tell me more about that.
So monitoring is all about collecting data about how your system is performing.
Okay.
Right. So things like, CPU usage, memory usage, network traffic, all those kinds of things.
Right, so it's like the vital signs of your system.
Exactly. And by monitoring those vital signs,
Right.
you can get an early warning if something is starting to go wrong.
Okay, so it's like having those sensors in place that can detect those problems before they become major issues.
Exactly. And a good monitoring system will not only alert you to those problems, but it'll also give you the information you need to diagnose and fix them.
So it's not just about like knowing that something's wrong. It's about like having the tools and the data to figure out what's wrong and how to fix it.
Exactly.
Okay, so monitoring is a big one. What else?
Another important thing is to have good documentation.
Okay, documentation. I know that's not always the most exciting part of software development,
No, it's not.
but it's definitely important.
Yeah. But it's essential for maintainability.
Right, so it's not just about making the system reliable today. It's about making sure that it can be maintained and supported in the long term.
Exactly. And good documentation will help the people who are responsible for maintaining the system to understand how it works
Right.
and how to troubleshoot problems when they arise.
So it's about making sure that that knowledge is captured and shared.
Right. And it's also about making sure that the documentation is kept up to date.
Right, because like systems change over time.
Exactly. Yeah. So you need to make sure that the documentation reflects those changes.
So documentation is an ongoing process.
It is, yeah.
Yeah.
It's not just something you do at the end of the project.
Right. It's something that needs to be integrated into the entire development process.
Exactly. And there are tools and techniques that can help you with that.
Okay, cool. So we've talked about monitoring and documentation. Any other like key strategies for building reliable systems?
Well, another important thing is to have a good process for incident management.
Okay, incident management. What's that all about?
So incident management is basically the process you follow when something goes wrong.
Okay,
Right. So, how do you detect the problem?
right.
How do you communicate it to the right people?
Okay.
How do you diagnose it?
Mhm.
How do you fix it?
Right, so it's about having a plan in place for when those inevitable failures happen.
Exactly. Yeah. And a good incident management process will help you to minimize the impact of those failures
Okay.
and to recover from them as quickly as possible.
So it's not just about like, fixing the problem. It's about like minimizing the downtime and like getting the system back up and running as quickly as possible.
Exactly. And it's also about learning from those incidents.
Okay.
Right. So once you've resolved an incident, you need to take some time to figure out what happened, why did it happen, and how can you prevent it from happening again.
So it's about like continuous improvement.
Right. And it's about using those failures as opportunities to learn and grow.
Okay, so incident management is a really important part of building reliable systems.
It is.
And it's about more than just fixing problems. It's about learning from them and preventing them from happening again.
Exactly.
So we've talked about a lot of different strategies for building reliable systems.
We have.
And it sounds like there's no like one-size-fits-all solution.
Right. It really depends on the specific application you're building
Right.
and the specific risks that you're facing.
So it's about like taking a holistic approach,
Mhm.
understanding the different failure modes,
Yeah.
and then choosing the right strategies to mitigate those failures.
Exactly.
And it's about like recognizing that failure is inevitable
Mm-hmm.
and building those systems that can handle it gracefully.
Right. It's about building those resilient systems that can adapt and recover.
All right, well, that was a really fascinating deep dive into reliability.
Yeah.
And I think it's a really important topic for like anyone who's building those software systems.
Yeah.
So next up, we're going to be talking about scalability
Okay.
and like how we can build those systems that can handle those like ever-growing demands of like data and traffic.
Right.
So stay tuned for that.
Sounds good. Yeah, and we need to think about how we measure that performance too, right? Like how do we actually know if we're meeting those demands,
Yeah, that's a great point. I mean, response time is obviously a big one,
Yeah.
right? Especially for web applications where, every millisecond counts.
Yeah, response time is definitely crucial, especially for those user-facing applications, where users expect things to happen instantly. But it's not enough to just look at the average response time.
Oh, really?
Yeah, we need to think about those higher percentiles, like the 95th or the 99th percentile,
Okay.
to really understand how those tail latencies are affecting those users who might be having a bad experience.
Right. So it's not just about the average user. It's about making sure that even those edge cases, those users who are experiencing those slower response times are still having a good experience.
Exactly. Yeah. It's about understanding the entire distribution of response times, not just that average.
Yeah, that makes a lot of sense.
Yeah.
So what are some of the things that can cause these tail latencies, these slow requests?
Oh man, there are so many things. It could be the amount of data a request needs to process. Like if you're querying a massive database,
Right.
it's going to take longer than if you're just fetching a small piece of data.
Right.
But even seemingly identical requests can have wildly different response times due to things like context switching between processes,
Hmm.
network hiccups, garbage collection pauses, even things like disk seek times.
Disk seek times. Now that takes me back to my computer architecture class.
Yeah, it's amazing how those low-level details can still have an impact on performance in these complex systems.
Yeah, it's like, we think about all this high-level stuff, but sometimes it's those tiny little details, those low-level things that can really trip us up.
Exactly, and that's why it's so important to have those tools and techniques to measure and analyze performance.
So what kind of tools are we talking about here? Are there like specialized algorithms or techniques for efficiently calculating those percentiles without putting too much strain on our systems?
Yeah, absolutely.
Yeah.
There are algorithms like forward decay, t-digest, HDR histogram, all these fancy names, but they basically allow you to calculate those percentiles efficiently without having to store and sort all that data.
Okay, so it's like we can get those insights without having to sacrifice
Yeah,
performance.
exactly. And once we have those metrics, we can build those monitoring dashboards that give us those real-time insights into how our applications are performing.
Dashboards. I love dashboards. It's like, you're sitting in that mission control center,
Yeah.
watching all those graphs and charts.
Yeah, it's like you're at the helm of a starship,
Exactly.
monitoring all the vital signs of your application.
So dashboards, they're not just about looking pretty. They're actually about giving us those actionable insights.
Exactly.
Yeah.
No, they help us to pinpoint those performance bottlenecks, track down the root causes of those slow requests, and understand how performance changes over time.
So it's about turning that raw data into something that we can actually use to make decisions.
Precisely. And those decisions often lead us to the big question, scaling up or scaling out.
Okay, yeah, that's a classic question.
Okay.
So let's break that down. I know scaling up, sometimes called vertical scaling, is basically about beefing up our existing server,
Right.
giving it more RAM, faster processors, like souping it up.
Yeah, it's like giving your race car a bigger engine.
Exactly.
Right.
But at some point you hit a limit, right?
You do. Yeah, there's a ceiling to how much you can scale up a single machine.
Right.
No matter how powerful it is, eventually you're going to need to distribute the load across multiple machines. And that's where scaling out or horizontal scaling comes in.
So instead of one superpowered race car, we're now talking about a team of race cars, each handling a portion of the track.
That's a great analogy.
Yeah.
Scaling out can be more complex than scaling up, especially when you're dealing with stateful systems.
Stateful systems. Yeah, we touched on that earlier, but let's dig into that a bit more. What exactly makes a system stateful, and why does it matter so much when we're talking about scaling out?
So a stateful system basically remembers things. Think of a database.
Well,
It stores data, and that data represents the state of the system.
right.
Scaling out stateless systems is relatively straightforward because each request can be handled independently.
Okay.
But when you have data that needs to be consistent across multiple machines, things get a lot more complicated.
Right. So it's like if you have multiple servers, each with its own copy of the database,
Yeah.
you need to make sure that they're all in sync.
Exactly. And that introduces a whole bunch of challenges like data consistency, making sure that all those machines have the same view of the data, even if some of them are temporarily unavailable.
Right. And then there's also the issue of fault tolerance, right?
Right. Absolutely. Yeah. If one of those servers goes down, you don't want the whole system to crash.
Right.
You need mechanisms to handle those failures gracefully, perhaps, by replicating data across multiple machines so that even if one goes down, the data is still available elsewhere.
So scaling out stateful systems is definitely not a trivial task.
It's not. It requires careful planning and a deep understanding of those challenges involved.
This makes me appreciate just how complex building these scalable systems can be. It's not just about throwing more hardware at the problem. It's about carefully considering the nature of our data, understanding the trade-offs between different scaling approaches, and designing systems that can handle those complexities.
You got it. Scaling is not just a technical challenge, it's an architectural challenge. It requires us to think about the big picture and make those decisions that will allow our systems to grow and adapt over time.
And that brings us back to maintainability, right? Like we've talked about operability, simplicity, and evolvability as these key principles. But what are some practical steps we can take to build systems that are truly a joy to work with, not just today, but for years to come?
One of the simplest yet most powerful things you can do is write good documentation.
Documentation. I know it's not always the most glamorous part of software development.
It's not, but it's absolutely essential for maintainability. Think of it as a roadmap for your fellow engineer, guiding them through the intricacies of your system.
So good documentation. It's like leaving those breadcrumbs for the people who are going to come after you.
Exactly. And good documentation should go beyond just describing what the code does. It should explain why those design choices were made, the assumptions that were made, potential pitfalls to watch out for.
So it's about providing that context, that understanding that helps people make sense of the system.
Precisely. And to make documentation less of a chore, integrate it directly into your development workflow.
Okay, how do we do that?
Tools like docstrings allow you to embed documentation directly within your code itself.
Oh, that's interesting. So it's like you're writing the documentation as you're writing the code.
Exactly. And that makes it much easier to keep it up to date. Because as we know, systems change over time and documentation can quickly become outdated if it's not treated as an integral part of the development process.
So it's about shifting our mindset from seeing documentation as an afterthought to treating it as like a first-class citizen in our development process.
Exactly. And alongside good documentation, we need to strive for simplicity in our code. This is where those powerful abstractions come in.
Abstractions, yeah, we talked about them earlier as a way to like hide complexity. But how do they actually contribute to maintainability in a practical sense? Can you give me some examples of good abstractions in the world of data systems?
A good abstraction encapsulates complex functionality behind a clear, concise interface.
Think of SQL.
SQL, yeah, the language we use to interact with databases. Exactly. It allows us to interact with databases using a relatively simple language without having to worry about those low-level implementation details.
Right, so instead of writing complex low-level code to manage files and data structures, we can express our intent more declaratively using SQL queries.
Precisely. We tell the database what we want, and it figures out how to do it. Good abstractions like this promote code reuse, reduce the potential for errors, and make systems easier to understand and modify.
It's like having a well-organized toolbox.
Yeah.
Each tool has a specific purpose and a clear way to use it, making it much easier to find the right tool for the job and avoid the frustration of rummaging through a jumbled mess.
I love that analogy. And just as a well-organized toolbox makes a mechanic's life easier, good abstractions simplify a developer's life.
So it's about creating those clear boundaries, those well-defined interfaces that make it easier to reason about our systems and make changes without breaking things.
Exactly. And that brings us to the final piece of the maintainability puzzle, evolvability. How do we build systems that are flexible and adaptable to those inevitable shifts in the software landscape?
Evolvability. Yeah, we talked about that earlier as the ability to adapt to change, but how do we actually bake that into our systems?
One key principle is modularity.
Modularity. Are we talking about breaking down our systems into smaller, self-contained pieces?
Exactly. By decomposing your system into well-defined modules with clear interfaces, you make it easier to modify or replace individual components without affecting the entire system.
So it's like building with Lego blocks instead of pouring a giant concrete monolith.
That's a fantastic visualization. Modularity allows you to isolate those changes, making it easier to test and deploy new features without introducing those unintended consequences.
Right. So if you need to make a change, you can focus on that specific module without having to worry about the entire system.
Exactly. And it also promotes code reuse. If you have a module with a well-defined interface, you can use it in multiple contexts, saving you time and effort.
So modularity, it's not just about making systems easier to maintain, it's also about making them more efficient to develop.
Absolutely. And it's about embracing the fact that software is a living, breathing entity that needs to evolve over time.
So we need to design our systems in a way that allows for that evolution, that makes it easier to adapt to those changing requirements.
Precisely. And that brings us to another aspect of evolvability that's often overlooked, the human element.
The human element, I'm intrigued. What do you mean by that?
Evolvability isn't just about technical choices, it's also about creating a culture that embraces change and empowers developers to contribute to the evolution of the system.
So it's about fostering a collaborative environment where developers feel comfortable proposing changes, experimenting with new ideas, and continuously improving the system.
Exactly. By creating a culture that values learning, experimentation, and continuous improvement, you set the stage for a system that can truly evolve and adapt to those ever-changing needs of its users.
It's like creating a garden where those ideas can flourish and grow.
That's a beautiful way to put it. And just like a garden needs constant care and attention, A culture of evolvability requires ongoing effort and nurturing.
So it's not just about the code. It's about the people and the processes that surround that code.
Absolutely. It's about creating an environment where innovation can thrive and where the system can continue to evolve and improve over time.
This has been an incredibly insightful exploration of maintainability. It's not just about writing clean code. It's about understanding the human factors, embracing modularity, and fostering a culture that embraces change. It's clear that maintainability is not an afterthought. It's a fundamental principle that should guide every stage of the software development process.
I completely agree. And remember, a well-maintained system is a joy to work with, and it ultimately leads to software that is more reliable, scalable, and adaptable to the inevitable challenges of the ever-evolving tech landscape.
And that's something that every developer should strive for.
Absolutely. Well, not quite. They're still there.
Yeah.
But you don't have to think about them. The cloud provider handles all that infrastructure stuff, so you can just focus on your code.
So it's like it takes care of all the the server stuff, the operating system, all that jazz.
Yeah, all that stuff. That can be a real headache. You just write your code, deploy it, and the platform takes care of the rest.
Wow, that sounds pretty amazing, especially for those applications where, the workload can vary a lot.
Yeah.
Or you need to be able to scale up really quickly.
Exactly. It's like having an on-demand workforce, you know? You only pay for what you use.
Right, so it's super efficient.
Mm-hmm.
But I know we talked earlier about some potential downsides like security concerns and maybe vendor lock-in. Are there any other challenges that we should be aware of with serverless?
Yeah, I think one of the biggest challenges is that it requires a bit of a shift in thinking.
Okay, how so?
Well, traditional applications are often designed to run continuously, on those dedicated servers.
Right, they're just like always on.
Exactly. But serverless functions are triggered by events. They execute for a short period, and then they shut down.
Ah, so it's a more event-driven approach.
Yeah, and that can have a big impact on how you design and structure your application.
So it's like instead of having this big monolithic application that's always running, you have these smaller, more modular pieces that are triggered by specific events.
Exactly. It's a different way of thinking about application design.
So it sounds like there's a bit of a learning curve there.
There is, but once you get the hang of it, it can be a really powerful way to build applications.
And what about performance? I know we talked about latency being a potential issue.
Yeah, that's something to be aware of. If a function hasn't been executed recently, it might need to be loaded from storage, which can add a bit of a delay.
So there's a potential trade-off there between scalability and performance.
There can be, but the cloud providers are constantly working to improve those cold start times.
Cold start times, what's that?
It's basically the time it takes to load a function from storage and get it running.
Oh.
And they're using techniques like function pre-warming and optimized execution environments to make those cold starts as fast as possible.
So it sounds like those performance issues are becoming less of a concern.
They are. And the benefits of serverless in terms of scalability and efficiency are hard to ignore.
It's definitely an exciting area to watch. And it just goes to show how important it is for developers to stay curious and keep learning.
Absolutely. The tech landscape is constantly evolving, and we need to be adaptable and embrace new approaches.
Couldn't agree more. Well, this deep dive has been an incredible journey, exploring those core principles of building those robust, scalable systems. I feel like we've covered so much ground, from those key qualities, reliability, scalability, maintainability, to all those practical steps involved. We talked about handling failures, the complexities of distributed state, the power of abstractions, good documentation, even that human side of software development.
It's been a fantastic conversation. I think our listeners are walking away with a lot of valuable insights.
Absolutely. And, as we wrap up, I just want to leave everyone with this thought. We've been talking about these principles in the context of data-intensive applications, but they really apply to any kind of software you're building, whether it's a mobile app, a web service, an embedded system. Those principles of reliability, scalability, and maintainability are always going to be important.
Absolutely. They're the foundation of good software design.
Exactly. So as you embark on your next coding adventure, remember what we talked about today. Keep experimenting, keep learning, and until next time, happy coding, everyone.